The grand rule of solubility is like dissolves like. We should make note of that. Like dissolves like. And by that we mean polar molecules dissolve in polar solvents. Nonpolar molecules dissolve in nonpolar solvents. And so when you think about water, now we know that water is very polar. On a water molecule, the oxygen end, here kind of shown by the red atom, the oxygen end is slightly negative because oxygen has a really strong electronegativity. It pulls on the electrons from hydrogen, leaving the hydrogen end of a water molecule partially positive. So you put a whole bunch of water molecules together and they're very attracted to each other. The same thing happens with anything that's got these charged regions. So if we know water is polar, very polar. So anything else polar will dissolve in water. And obviously we can also have nonpolar solvents, but water is probably the most common solvent that we would ever use. And so when I think about water being polar, well, what other types of particles are polar? Ionics. Ionics are polar. So ionics are as polar as it gets, where we're not even talking partial positive and partial negative. It's a full transfer of electrons, giving us like really charged ions, fully positive and fully negative ions. So ionics definitely dissolve in water. So do any other polar molecules. So ionics are polar, they'll dissolve in water, and other polar molecules also dissolve in water. So it's got to have something that's charged, whether it's a full positive or negative ion, or it could be like these partial positive and partial negative regions. In order to dissolve in water, you have to be really attracted to the water molecules. So since water molecules are charged, anything else with a charge will be very much attracted to the water molecules. But here they're giving us the example of a nonpolar compound like hexane. So hexane kind of looks like this. It's 6 carbons, 1, 2, 3, 4, 5, 6, and then they're totally surrounded by hydrogen. There's gonna be a lot of them. Think about 14. So every carbon will get his octet. They'll all have 4 bonds, all single bonds to hydrogen. Hydrogen, and one more hydrogen. Now, in this compound, the bond between carbon and hydrogen is slightly polar, but they're all arranged evenly around that central carbon chain. So we were looking at this molecule quite a bit in the past, CH4. And same thing, it's like that cute little tetrahedron. And so even though the bonds are polar, they're arranged in a way so that they cancel. And so even if there is maybe a little pull, there'd be a balanced pull at opposite directions. And the same thing kind of happens here. It's just that there's not one carbon in the middle. There's 6 carbons in the middle. But there's always a balance. There's a balance, there's a balance. Everything is symmetrical, even these guys on the ends. And so when all the little poles balance each other out, overall the molecule ends up being non-polar. So it's very similar to just a little CH4 molecule, it's just a little bit bigger. But we know that like water and oil don't mix, and this hexane molecule is kind of similar in that it doesn't mix with water. Well, yeah, it's because these molecules are non-polar, and so they're not really attracted to water molecules. When they're non-polar, they don't have any regions of charge, So then the water molecules end up being more attracted to each other, and they're really not interested in mixing with these non-polar hexane molecules, or it could be an oil molecule. Instead, they'd rather hang out with each other, where there are strong attractive forces. So the water molecules just don't mix. Some other examples in question 38. Consider this list of compounds. Circle the compounds that are most likely to dissolve in water. What information did you use to make your prediction? Okay, well, here's an easy place to start. There's two types of molecules that will dissolve in water. Which will dissolve in water? Either ionics or other polar molecules. So the ionic one is kind of easy to tackle because ionics are metal bonded to nonmetal. So if you look at the list of compounds and you see anything that's a metal, it's for sure going to be an ionic compound. It's got fully charged ions and it's going to dissolve in water. So for example, when I see magnesium and sulfate, magnesium is a metal. So yeah, magnesium sulfate, this should dissolve in water. Magnesium is a +2 ion and sulfate is a -2 ion. So remember what happens when we put this in water? The ions dissociate. And so you'd get like these separate magnesium +2 ions. And then it's a little bigger, but you'd also have the sulfate -2 ions. And the water molecules will surround each ion so that opposites attract. And so if I have a positive ion, it's going to be the negative oxygen region of a water molecule that's attracted to the positive ion. So my oxygen is the negative. There we go. And we call that a shell of hydration, where these water molecules would totally surround the ion. Obviously, there'd be more than 4 in the real world. And then it makes that ion really stable. Now, with a negative ion, your water molecules will orient themselves so that the positive hydrogen end is attracted to a negative ion. Even if it's a polyatomic ion like sulfate, it's still very charged and very attracted to the water molecules. There's my little shells of hydration. Opposites attract. So it's important to know that the oxygen end is always partially negative and the hydrogen end is partially positive. All right, anything else with a metal? Let's see, carbon and hydrogen are non-metals. Oop, calcium. Here's another one. Calcium oxide. That just, again, happens to be a +2, -2. Obviously, it doesn't have to be +2, -2. It could be anything that's got a charge. +3, +1, -3, -1, any of them. Yeah, those guys are going to dissolve in water, and calcium oxide would dissolve in the same fashion. Now, the other two, I don't know. They could be polar molecules. We might just need to draw them so that we can look at the structure and check out the arrangement of the atoms around the center. So I've got this C2H2. All right, so the carbons probably go in the middle because they can make the most bonds. Hydrogen would never go in the middle because he can only make one bond. Okay, so I guess for sure I'm going to link them up somehow. I'll just connect the dots. Then I've got 2 hydrogen. Well, with only 2 hydrogen and 2 carbons, we should make this as symmetrical as possible. We should be fair to each carbon. Okay, so you each get a hydrogen. But then that's all I got. So can you kind of see what we'll do in the middle? We can just triple bond. We'll triple bond the carbons. So here's my C2H2. And while I'm at it, let's sketch the CH4. Let's see if I can squeeze that guy down here. This one feel like we've drawn plenty of times. CH4, piece of cake. We'll hook on 4 single bonded hydrogen. 1, 2, 3, 4. There we go. Let's look at that guy first. The CH4 we know is a tetrahedron. There's a carbon in the middle. The carbon's got his octet, and he's got 4 bonding regions, and they're all bonded to the same atom. So when we've got a tetrahedron, there's nice even angles and equal distribution of electron groups around the center. And because it's the same atom, all of the little poles from those 4 bonds are exactly the same. So here's one of those molecules that could have polar bonds, but because they're arranged equally around the central atom, those little polar bonds cancel, and this ends up being a non-polar molecule. Non-polar molecule. Nope, not you. You're not going to dissolve in water. The other one, the C2H2, doesn't technically have a central atom. It's kind of like 2 atoms in the center. There's 2 carbons in the center. And if I look at each carbon, they kind of have the same thing going on. Each carbon has a triple bond to another carbon and then a single bond to a hydrogen. If you split that molecule in half, if I take this guy and I split it in half, can you see that each half is exactly the same? And so, yeah, the bonds, obviously in the middle between carbon and carbon, are totally non-polar. And there might be a little bit of a polar bond on the ends with the carbon and the hydrogen, but there's the same bond on the other side of the molecule. This is a linear structure. It's just kind of a longer linear structure. But when the molecule is symmetrical, like each half of the molecule has the exact same atoms, the same kinds of bonds, even if there's a little pull, it's going to cancel on the other side. And this guy is a nonpolar molecule. Nonpolar molecule. And it will not dissolve in water. The key is that we know water is polar. So in order to dissolve in water, you also have to have some kind of a charged region. Now, let's add to this list. What if they gave us something like this? What if I was given like HCl? Oh, well yeah, HCl, that's a simple one to draw. Hydrogen, whoop, chlorine's got 7 valence electrons. There we go. So yeah, HCl, it's a really simple molecule. It's only got 1 bond, and that 1 bond is very polar. Chlorine has a higher electronegativity than hydrogen. Chlorine's right next to fluorine. It still has 7 valence electrons and really wants to gain 1 more to fill his octet. So even though it's not ionic, it's still a polar molecule where the electrons in this bond are going to pull closer to chlorine, and chlorine would then become partially negative and hydrogen partially positive. So yeah, this guy's going to dissolve in water. This one would totally mix with water, where the chlorine end of the HCl molecule would be very attracted to the positive end of the water molecule. So now if I drew in like a little water molecule, it might align itself like this. And maybe there'd be another one kind of down here. Maybe there'd be another one up here. Yeah, water molecules are going to be attracted to that chlorine. Same thing on the other end with the hydrogen. That even though this isn't going to split to form ions, it's not ionic because it doesn't have a metal, the water molecules will still totally surround the HCl molecule, and they'll mix with the HCl molecules. They'll allow it into their world. Water molecules are like, yeah, you're polar? Come on in, let's mix. Around the hydrogen, we would just have the oxygen end. of the water molecule. And it might look something like this. But yeah, that guy's going to be attracted to water. It's polar. So it's any polar molecule. It could be something like this, that's HCl, any polar molecule. Yes, it'll dissolve in water. It'll mix with water. It'll be attracted to water. One other example might be something like your NH3. Where I say, okay, NH3, let's draw it. Which I might need to draw it to know, like, is this trigonal planar? Is it trigonal pyramid? 5 valence electrons on nitrogen. 3 singles, here they come. Oh, yeah. So here, when I draw it, I notice that there is that extra pair on the top. So I'm left with something that does not give me an equal distribution around the center. Because of that lone pair, this thing's polar. And now if I look at the periodic table, nitrogen should have the higher electronegativity. It's definitely closer to fluorine. The electrons will pull up toward nitrogen, meaning that the nitrogen region is partially negative, and the hydrogens will be partially positive. Will NH3 mix with water? Absolutely it will. Anything that's got those charged regions will be attracted to water molecules and should dissolve very well. So we're looking for anything ionic, metal, nonmetal, or any polar molecules, overall polar molecules, which might mean that I need to draw it so I can check the arrangement of the bonds around the center.